Let's start with consistency. For this, we first define what inconsistency is. Namely, an L-theory T is inconsistent if there exists a formula phi such that T proves phi and it also proves not phi. And the theory is then consistent if it is not inconsistent. And it turns out that if you prove one contradiction, right, so if you have one inconsistency in one formula, you actually become proof theoretically trivial, in the sense that if a theory is inconsistent, then you prove everything. So T formally proves phi for all phi. As usual, try to see if you can prove this yourself. Take a few minutes and see if you can come up with a proof. It is an important question, and a question that will return later and become very important then. So the question is whether we can decide, for example, by means of an algorithm, if a theory is inconsistent or not. Now, since proofs can use at most finitely many formulas, it follows that a theory T is inconsistent if this inconsistency already shows up in a finite subset of T, right? Because you can use at most finitely many formulas, so if you can prove phi and not phi at the same time, you can do this from a finite subset, namely the set of all formulas that you need to prove phi and not phi from T. Interestingly, we can also characterize provability itself through consistency. Namely, it holds that T proves phi if and only if I join not phi to T, that this theory becomes inconsistent. If you try to prove this now, you see that one direction is actually quite easy. Namely, if you know that T proves phi, right? But you also see that if you have T union phi, not phi, clearly proves, by the definition of proof, not phi, right? So if T proves phi, then T union not phi also proves phi, right? Because T already proves it. So, and since T union not phi also proves not phi, then we would have an inconsistency here. Now for the other direction, so if we assume that T union not phi is inconsistent, right? So that means, by the observation or proposition we had on the previous slide, that would mean T union not phi proves everything. So in particular, T union not phi proves phi. Well, that quite doesn't help us, because we need to show that this implies that T proves phi. We only can show that T union not phi proves phi. So how do we get rid of the extra assumption not phi here to show that T proves phi? Well, the trick here is a theorem that we can that we'll see on the next slide. It's called the deduction theorem, that allows us to pull this element over to the other side in form of an implication. So we will see that this will imply that we have that T proves not phi implies phi. And then to finish the proof, you use modus ponens together with a tautology, and the tautology is of the form not phi implies phi, that this implies phi. So this is a tautology. and I leave it to you to put the exact details then together. But again, the crucial property here is that we can go from this, that T union not phi proves phi, to that T proves not phi implies phi. And this, as I already said, is a consequence of the so-called deduction theorem. Often when we want to show an implication holds, the proof we come up with works as follows. We say, let's assume sigma, right? So let's assume we want to show the implication sigma implies phi. The proof would work, let's assume sigma holds. And then we show that phi holds too. So that would mean, right, we rely on the fact that proving an implication is the same as assuming the hypothesis and then showing that the consequence holds. That this is actually formally justified in our proof system is the subject of the deduction theorem. So the theorem is if T union sigma, where it's important here that sigma is actually a sentence, right? Phi can be any formula, but sigma has to be a sentence. So if T union sigma proves phi, that is equivalent to T proving the implication sigma implies phi. Regarding the proof of the deduction theorem, note that one direction is not very hard. This is pretty much a single application of the modus ponens. So simple application of modus ponens. The harder direction is the one that we needed in the previous theorem, namely to go from here to here. So for this direction, we suppose that T union sigma proves phi, and we let phi 1 up to phi n be a T union sigma proof of phi. And the way this proof then usually works is that you show by induction that for every I less than equal to n, T proves sigma implies phi I. And so you work your way through the proof and show that at each instance, right, so at each step of the proof, you actually have this implication here provable from T. And you do this by distinguishing the cases, so case distinction, depending on how the formula phi I was obtained in the proof, right, in the proof sequence. So it can be either through a logical axiom or because it's an element of T union sigma here, or by means of a rule. And I'm going to show you how to do it for one case. So the first case would be, for example, that phi I is a logical axiom. So in that case, you can proceed simply by saying, okay, we have a tautology. So the tautology would be phi I implies sigma implies phi I, right? And you know T proves phi I because it's a logical axiom, right? So any theory proves any logical axiom, and you know that this is a tautology here. So the rest is a simple application to these two things here of the modus ponens. So I leave the other cases now up to you. So you have to see how you can find a similar argument to this one. You have to, in some cases, have to find the right tautology. It's not always going to be this tautology. There are other tautologies that you need to employ here. Also, at some point, you will need the fact that sigma is a sentence. So be aware of that and see where do we actually need that. As you may be able to guess, it has to do with the case where you apply a universal generalization rule, because remember, if we looked at the universal or generally the quantifier laws or validities, for one law we had the condition that a variable could not appear freely. And a sentence, of course, gives us the guarantee that no variable appears free. Recall from the last lecture where we defined examples of theories, there was one specific example where we started actually out with a structure and then collected all the sentences that are true in this structure in a theory. This was the theory of M, the structure M, and it's also called the complete theory of an L structure M. Note that the theory of a structure is always consistent. And that's because, well, suppose theory proves phi, and it also proves at the same time not phi. Well, then by soundness, right? Remember, we had this property of a proof system, of our proof system called soundness, that if you can prove something, it actually also gives us logical implication. Well, that would also mean that the theory would imply logically imply phi and also logically imply not phi. But if you think of the definition of this, this is actually impossible, right? Because this says whenever I have a model for the theory of n, then this also would have to be a model of phi. And at the same time, whenever I have a model of this also would have to be a model of not phi. But in a structure, only one of the two can hold. So it is impossible that in a structure both phi and not phi hold. So that's why, via soundness, the theory of a structure is always consistent. So if I derive a theory from some specific concrete mathematical object, we always get something consistent from it. Besides being consistent, the theory of a structure also satisfies the following. For all L sentences sigma, we have either T proves sigma or it proves not sigma. And the reason for this is simply that the theory of M does this with respect to logical implication, right? So whenever I have a sigma here, a sentence sigma, it is true that either M satisfies sigma, or if it doesn't satisfy sigma because it's a sentence, it has to satisfy the negation of sigma. So we know that for every sentence sigma, either M satisfies sigma or M satisfies not sigma. So that means the theory already contains, the complete theory of a structure already contains for every sentence sigma either sigma or not sigma, right? And since it already contains this alternative, one of the two, it particularly means it proves one of the two. Now, generally, consistent theories with this property here, that they split the set of all sentences over a language into into two, depending on whether the theory proves it or not, right? Complete consistent theories with this property here, right? So this complete kind of splitting into true and false, or provable and not provable, right, are called complete. And so complete theories are in some sense mathematically very powerful, because they give us a complete classification of truth, right, with respect to it. They leave nothing undecided. And it is not surprising, therefore, because it's a very powerful property, that most mathematical theories are actually incomplete. It's a completely natural property to be incomplete. So, for example, take group theory, and you take the sentence that the group is abelian, right? The group axioms can prove neither sigma nor not sigma, right? Because if they could, then by soundness, every group would either have to be abelian or non-abelian, respectively, depending on whether it proves sigma or not sigma. But that's not true, right? There are groups that are abelian, and there are groups that are not abelian. So, in particular, the group axioms cannot decide this statement here in terms of a proof basis, right? So this sentence here is also called independent of the group axioms. So incompleteness is a completely natural mathematical property that we often encounter. And the question is then, which mathematical theories are actually complete, besides the kind of canonical example of being the theory of a structure? Right? So, to finish this off, the Gödel completeness theorem that we will encounter next does not say that every theory is complete, because as we saw here, there are plenty of examples of incomplete theories. So then you may ask, of course, what does the Gödel completeness theorem say then? And that will be the content of the next lesson.